How is this different from what we did last time? Okay, we got x and y to deal with, right? Two-dimensional. Okay, 2D kinematics. You got to be really careful in all of these problems that we're going to be dealing with. What is x stuff and what is y stuff? All right, that's going to be a big deal. So let's just start out with a little bit on vectors. You're going to really expand on this in Vector Boot Camp. Okay, so this is just a tiny little crash course on vector stuff we need to know to be able to do our 2 examples. So we're going to do that, and we're going to do 2 examples today, and that's our notes. Okay? All right, so vectors are a property with both magnitude and direction. Direction is self-explanatory. Magnitude just means the value. Okay? Size. And often on like UT homework or WebAssign or something like that, if it says the magnitude of, what do we drop in our answer? We drop the negative sign if it comes out negative, or we drop the angle if we're at some angle. Okay, 2 dimensions, not just negative, positive anymore. It's going to be angles. Okay, so some different things we're going to need with vectors. Okay, let's use a velocity vector as an example. Let's say something is going at 5 meters per second, and let's say it's going 30 degrees from 0. One of the things we're going to need to know how to do is break it up into x and y components. Okay, so we will take this vector and we'll break it up into x. We will break it up into y. Okay, and we just need to do a little simple trigonometry to do that. So this side, the y side, we can say is 5 times which trig function? It's the opposite side. We're going to use sine. So it's 5 sine 30. Okay? And I know you know how to punch that in, so we're just going to leave it like that. Okay, the x side would be the hypotenuse 5 times the cosine of 30 degrees. Okay, that's one thing we're going to need to be able to do is break vectors up into their parts. Vector Boot Camp will do more with you on that. Vector addition. Okay, let's say I have vector A, vector B. These could be displacement vectors. Vector C and vector D. And a good example of vector addition for that, if those were in meters, that might be like certain bearings that a hiker took. Okay, they walked around, and we always add vectors how? There's kind of a little saying. Tip to tail, have you guys heard that? Okay, so you draw them like that. You draw the start of this vector at the tip of that vector. Okay? Now our resultant vector is this one. Okay? Start from your origination point, and this is your resultant vector. So vector E would be resultant. Okay, and if these are position vectors, it's your final position from 0. All right, now we got to remember that this red line has both magnitude and direction. Vector Boot Camp's going to do a really good job of teaching you the math of how to get that value. Okay, have we done that before? Do we feel like we've conquered that in math? Okay. Vector Boot Camp's going to show you some more stuff on that. All right, so we're going to leave that alone, but that's kind of what's coming. Okay, one thing we do with this stuff is relative velocity problems in 2 dimensions. Okay, so you know that if Mr. Hicks is given any chance to do any kind of physics problem that relates to rafting, you know that I'm gonna take that chance. So obviously we got a river flow problem right here. All right, and in your book, this is kind of a good starting problem here. So we're going to draw a little length of river right here. And we're going to start going through these 4 parts. Okay, let's read. Example 1. Let's say the Colorado River is flowing at 4 meters per second during high water runoff. Let's say that we have a rafter that is capable of rowing 3 meters per second. If the river is 100 meters wide at a given location, they want to know all of these things. Letter A, how long would it take the rafter to cross if they point at a 90-degree angle to the current? Okay, this kind of problem we break up into X and Y. So let's look at our diagram here. We've got a current flow of 4 meters per second. Okay, and we're going to put a raft on this river. And it is capable of going 3 meters per second, and that's in any direction. So we pretend it's flat water. The person could row 3 meters per second in any direction. Okay, now that is relative to the water. All right, that's how we would say that, 3 meters per second. Okay, now in this example, they are going to point directly across the water. Now I'm going to draw this vector a little smaller than this one to indicate that its magnitude is smaller, 3 meters per second. All right, and our displacement. It's actually not our displacement, it's the width of the river. Our displacement is going to be something else. Okay, this is a 100 meter length right there. Okay, how long would it take? In part A, we are going to figure out the time. When we have a problem like this, setting it up is important. So we listed what we knew. We drew a diagram to list it on, and we put what we wanted to find out. We're going to split it up into X and Y. Let's just make a little table here. And we did this last year with what? Anybody remember? We did an XY chart and we listed stuff. Projectiles, that's exactly right. Okay. All right, so X information. We're going to treat this as the X direction, the river flow. All right, and we've got a velocity, I'm just going to call it Vx, equal to 4 meters per second. That's the river flow. Y direction, and that's all we know, by the way. Y direction, Vy, 3 meters per second. Notice nothing is accelerating in this example. Okay, this is constant velocity. We'll deal with acceleration another time in 2 dimensions. Okay, what else do we know about the Y direction? Delta Y equals 100. We'll put a unit. Okay, and that's all we know. We don't know time. Now, since there's nothing accelerating here, this is not that hard of a problem. Okay? Ideas on how to solve it. Luke? Distance over velocity. So let's put down an equation here. When we have a velocity, we're going to put Vy is equal to delta Y over t, and Luke just rearranged it, so we're going to say time is equal to our delta y divided by our y velocity. Okay, so we have to do 100 divided by 3. Math is easy. 33.3 seconds. Okay, did we even need the x stuff? No, we didn't. We don't even care about the flow of the river for this yet. All right, part B. I'm going to go over here. And let's work on part B. X, Y. Okay, part B asks us how far downstream would they be from their starting position. Okay, again, Vx equals 4. Vy still equals 3. Okay, and now we have a time. All right, so our time applies to both sides. In other words, the 33 seconds it took them to go in this direction, what else were they doing? They're getting swept downstream at the same amount of time. Okay, we want to find out how far downstream they are from their starting point. Okay, they're not going to go directly across the river because they're pointing directly across and the current's taking them down. Okay, so now we just have to do the same thing over here. Delta x is equal to the rate, or the velocity, times the time. Meters per second times 33.3. Okay, can somebody punch that one in for me? 133.332. Okay. 133.3 we'll call it, and we are in meters. Okay, so notice since the river is going faster than the person can row, they are further in the x direction downstream than they got in the y direction. Does that make some sense? Okay. Part C, what is their velocity relative to the shore? You're going to see this word a lot as we start to work out some of these problems. Relative to the shore this time. Let's go over to the back. Okay, if you are an observer watching this person from the shore, here's what you're going to observe. Let's draw a little picture. They're going to be going over at 4 meters per second. Okay. Across at 3. Okay, and their resultant velocity vector, all right, I'll use red for that. Their resultant velocity vector is right there. Okay, here's where we got to get a little triggy. All right, now what's that resultant vector? It's 5. It's a 3, 4, 5 triangle, right? Okay, so we don't even need to do anything with that on our calculators, but if it were more complicated, we would use good old Pythagorean theorem. Okay, now we're not quite done. All right, it's going to appear to someone on shore that they're going 5 meters per second. However, we also need an angle because vectors are magnitude and direction. Okay, so we need to solve for this angle theta here. All right, and you can just pick your favorite trig function. I always use tangent because if I mess this up, I still get the angle right, because I've got these two things. So tangent is TOA. My initials are CAH, which is the cosine thing, but I still go with tangent. Can you believe that? Okay, so what that means is tangent theta equals opposite. Okay, now the opposite side is 3. The adjacent side is 4. Okay, take a second in your calculator, see if you know how to undo a tangent and get theta by itself. Okay, if you get a reasonable answer, it's probably right. If you get a really small number, what is your mistake? You are in radians, okay? All right, if I had my little name tiles, I'd call on you guys. Let's see, how about you guys? What'd you guys get? 36.87? Yeah, okay. Theta equals 36.87 degrees. Okay, so here's how we're going to write our final answer. Part C, the velocity is 5 meters per second. And then I like the little at symbol at 36.87 degrees. If you put an answer like this, where am I assuming your starting point is? 0. Okay, right there. Now, the other thing we'll do is north, south, east, west. Okay, and you could say some angle from north. Okay, and give me that angle right there from north. Okay, so we'll do some of that as well. And that in the navigation world is called a what? Anybody? A bearing or a heading. Yep. Okay. I don't know if there's a difference between those two, bearing, heading. All right, letter D. Okay, what is their displacement vector? Okay, let's draw another triangle. We've got our x displacement. I always like to draw x first. Okay, and this was 133.3. The y was 100. Okay, and I'll just let you guys solve that one from there.